Hey, hi. Hey, one major topic we haven't hit yet, or we haven't hit real thoroughly, is periodicity. So, some of this will be a review from your first year chem course. I'd also really would like you to really encourage you to look at a PowerPoint that I'll have on my Blackboard, and I'll probably email it to you as well. I tried to take the one I had from last year and make it a little bit better for you. There'll be a lot of information on that, okay? So periodicity. I think I'll break this up into two different little videos. We want to first talk about atomic radius and ionization energy. So I hope you see this is the periodic table. I'm leaving out the transition metals. So we have the representative elements, the S block and the P block. These are noble gases, alkali metals. I don't have this guy. So that would be beryllium, hydrogen, lithium, sodium, potassium, okay? So this is really helpful, first of all, just realizing that the largest atom, the atom with the largest atomic radius is going to be in the bottom left-hand portion. It's going to be francium, okay? So just knowing that can help you answer a lot of questions with regards to these two trends. So as you go down a group, atoms get larger. When you go across a period or family, okay, let me write this down. Period. No, it's not just a period. Excuse me. These are families. Groups are families or are groups. Okay. So columns are families or groups, and then these are just periods. Rows are periods. Sorry about that. Okay, so let's look at the reason why atoms get larger as you go down a group. You may know this already. Let's look at lithium. Let's look at lithium and sodium. Okay, so what do we know about sodium? Or lithium. Let's go lithium first. We have three protons in the center, in the nucleus, 3 protons. We have 2 electrons in the first outer energy level, and then we have an electron on the second energy level. Of course, it's 1s2, 2s1. So we have 2 on the first energy level, just 1 on the second energy level. It has a 1 valence electron. So sodium, if you look at sodium, has 11. Sodium has 11 electrons, 11 protons. So 11 protons. We'll have 2 electrons on the first energy level. We'll have 8. 1, 2, 3, 4, 5, 6, 7, 8. And then we'll have a third energy level, okay? So, one thing you can think of is that the sodium is going to be larger just because there are more energy levels, and that just takes up more room, okay? So, as you go down a group, one of the reasons they get larger is you just have another energy level, and that just takes up some space. Now, there is another reason. A lot of people would call it electron shielding. And I think in the PowerPoint, maybe I call it electron shielding. I don't really like that. If you think about this electron, of course it's being attracted to the nucleus, okay? But what are all these electrons doing to this electron? That's right, they are repelling it. So I think electron shielding is a kind of a cop-out, and I'm trying to understand. So all these electrons are repelling, pushing this electron out. So it's actually possibly a little bigger than if you just take into consideration the energy level and the number of protons, okay? Hey, the attraction here, don't forget, I think we went over this just real briefly. The electrostatic attraction between the electron and the nucleus. Remember, the force of attraction is directly proportional to the charge of an electron times the charge of the nucleus. I'll just put 2 there. Divided by the radius squared, or let's put the distance squared. Okay. So if we were to double one of these, it would double the force. If we keep this constant, let's see, keep the distance constant, we double both these, it'd be 4 times the force. If we keep these the same, but double the distance, what happens to the force? Yeah, it's 1/4 as great. It's inverse square law. So I'll mention this again in another video when we look at melting points of various ionic compounds. All right, how about going across a period? So let's grab, when we look at a nitrogen and oxygen, maybe that'd be good. Nitrogen and oxygen, that's fluorine. So oxygen, 8, and nitrogen, let's look at those guys, okay? So why is oxygen smaller? All right, so we're adding another electron. Oxygen has another electron, but that's right. What's different about oxygen also is that it has a greater nuclear charge. It has 8 protons. So this charge is greater. All right, now, another way of thinking about this is that is what's called effective nuclear charge. If we define effective nuclear charge, so effective nuclear charge is equal to the, let's say, atomic number minus the number of core electrons. Okay? Okay, so for nitrogen, the effective nuclear charge for nitrogen, so for nitrogen, the effective nuclear charge for nitrogen would be, it's 7 minus, now let's think about nitrogen, 1s2, 2s2, 2p3, right? Yeah. So it has 5 valence electrons, it has 2, so these 2 are the core electrons, minus 2, so this is plus 5. So the effective nuclear charge for nitrogen is plus 5. Kind of like the charge it feels. The charge that the outermost electron feels. The effective nuclear charge for oxygen is, okay, it's 8, and it still has just 2 core electrons, so it's plus 6. So this effective nuclear charge for oxygen is greater. That's another way of thinking about why, as you go across a period, atoms get smaller. What we're doing is increasing this Q, increasing the charge of the nucleus, so that attractive force is going to be greater, and that'll, okay? All right, that's atomic radius. Let's think about ionization energy. Ionization energy. Let me just erase this real quickly. Excuse me. Ionization energy. Energy needed to ionize something. So let's just write up here. What we want to do is, if we have element X and we add a certain amount of energy, we can kick an electron out, the valence electron, and then what we obviously get is a cation. Okay, so we're kind of oxidizing the element or the atom. IE stands for ionization energy. So I thought what we do is just let's look at what happens when you go down a group. If you think about, this is beryllium here, and this is what is this? Magnesium. So if you think about plucking off these electrons, which one's going to be harder? This electron or this electron? The nucleus is here. So look, this distance is greater, so the attractive force is much less. So this is going to be easier. Generally speaking, right? The further the electron is from the nucleus, the easier it is to ionize. The ionization energy would go down. So in general, The size is inversely proportional to the ionization energy. Now there's exceptions to that. If you go across a period, what generally happens? Atoms get smaller. So you think about removing this valence electron, right? It's gonna generally increase. All right. Now, there's some exceptions. Let's look at nitrogen and oxygen again. Okay. Let me just put these things down. Sorry about that. Okay. So nitrogen and oxygen. All right. If you look at nitrogen, it's outer. So it has. If we use Hund's rule, look at the p orbital. We have 1, 2, 3. So we have 3 half-filled p orbitals. Okay. Oxygen would have 1, 2. Remember the bus rule? All right. So we have 2 half-filled, 2 bonding sites here, and here we have a filled orbital. So you would think that, based on the size, the ionization energy for oxygen would be greater because it's smaller than nitrogen, but that's not the case. Let's look at this. You see that orbital? There's 2 electrons in that orbital. What are these electrons doing to each other? Yeah, they're repelling each other. So this electron that we're going to remove is already getting a head start. It's already getting kicked out by this electron. So it turns out the ionization energy for this is less than the ionization energy for nitrogen, despite the size. All right? That happens in a couple places. This is a great example. So nitrogen's family versus oxygen's family. By the way, the fancy name for oxygen's family, it's called the chalcogens. The oxygen family, in general, their ionization energies are going to be greater than nitrogen's. And it's due to this fact right here. A lot of people want to say, hey, electrons like to have, or atoms like to have half-filled orbitals. Yeah, but this is more the reason. This oxygen is lower. It doesn't fit the trend because these electrons are repelling each other, okay? Okay, I think we should just mention real quickly second ionization energy as well. Second ionization energy. So let me make some room here, and we'll look at the second ionization energy. I can't go over 15 minutes, or I can't upload it to YouTube. Otherwise, I have to pay for YouTube, I think. Okay, so I think we could let's look at sodium and magnesium. So of course, the second ionization energy would be if you already removed an electron and you add this another energy. Of course, it's going to be great. It's going to be greater because that electron is going to be closer to the nucleus. Second ionization energy, what you can do is it can go from +1 to +2 if you remove another electron. So second ionization energy. Ready? Here we go. Let's look at sodium and magnesium. So sodium. 1s2, 2s2, 2p6, 3s1. Okay, magnesium. 1s2, 2s2, 2p6, 3s2. Okay, so when looking at second, third, fourth, fifth ionization energies, I'd like to encourage you to write the electron configurations. You can use the noble gas abbreviation, doesn't matter. And then think about take away one electron. So in the case of sodium, let's remove this valence electron. Now we're going to have a sodium ion. Magnesium, let's remove this electron. And then look at what's left over. Look at this. Which one's going to have a higher second ionization energy? Yeah, absolutely, sodium. I mean, it is it's good to go. It's isoelectron with neon, second energy levels filled. This 3s electron is out pretty far away from the nucleus, will be easily plucked off. It's going to be hard to break into this.